Hello everyone, I am our CDT theory and simulation course. I'm a bit pissed off here because I've just been talking for 10 minutes and then realized the sound recording's not on. Well, never mind, starting it from where it's supposed to be starting. So we'll be doing today further programming. Again from scratch, but this time of a fairly complicated experiment that is a field sweep NMR experiment. Now, field sweep goes back to fairly old days, 1950s, maybe even earlier than that, when the electronics wasn't fast enough and the pulsed NMR wasn't yet invented. And so what people were doing is irradiating the sample at a particular frequency, either microwave or radio wave, and looking at the system response while they were sweeping the magnetic field. And sweeping the magnetic field means that different frequencies, resonant frequencies that the system has, would each come into resonance with a static irradiation frequency in turn. And so we are getting, in a way, an NMR or an EPR spectrum, except we're getting it not in the way that modern spectroscopists are perhaps accustomed to. One particular thing that this makes difficult from the simulation perspective is that we require a steady state of the system. And the steady state means we need to wait for an infinite time, and that's a bit hard from the simulation perspective. So what we need to do first is to do a little bit of mathematics to get that problem recast in a way that's computationally tractable. Now, if you look into textbooks, what you'll find is something called the Fermi-Golden rule, which says diagonalize the Hamiltonian, compute the transitions, and blah blah blah. That is probably the worst possible way of doing it, because the line width isn't properly factored in. There are multiple approximations done on the way, notably the perturbation theory. So we'll be doing it the way that is fairly modern. It does rely on a fairly big computer being around, but it does have the advantage of not having a perturbative fudge. So, well, let's start with our standard Liouville-van Neumann's equation. I've dragged this mass-type window into my recording screen here. So we just say d by dt of our density matrix, which in Liouville space would be stretched into a vector. So it's something like that. Rho of t is just the thing we know, minus I, the Hamiltonian commutation superoperator, acting on the same thing. But what we also require for there to even be a steady state is some kind of dissipation. That is, we need our relaxation superoperator, about which we know quite a lot from the previous lectures by now. And that would be applied to the difference between the current density matrix and the steady state, the equilibrium density matrix of our system in the absence of all perturbations. So rho equilibrium, which we will just obtain by taking the exponential of the Hamiltonian, as I explained in a few lectures that we're dealing with relaxation theory. Right, so this is our time domain Liouville equation, but what we need for this is a steady state, and a steady state means that the time derivative is equal to 0. So we say 0 equals this minus IH blah blah blah. So this, and what we now need to do is to solve this for our density matrix, which would be the density matrix at infinity, that is at a steady state. Okay, so let me just open the brackets here. So what we've got is we get this out and put it here, minus another instance of relaxation superoperator times the equilibrium density matrix. There we are. What I'll do is I'll drag this over, rather drag this over here with a plus sign. And then I'll take rho infinity out of the bracket over here, and I'll put a bracket around this, and then we got that. So to solve this for rho infinity, we need to take this to the minus 1 and apply it here. So minus 1. And to just turn the whole thing around to make it a little bit more convenient looking, I'll just move this here. There we are. So our row infinity is the inverse of this matrix times the relaxation superoperator times the equilibrium density matrix. And just to remind you what the equilibrium density matrix was, it was our row equilibrium in Hilbert space. Equilibrium was just the Boltzmann law. It was exp minus kt in the denominator and the Hamiltonian operator in the numerator, and all of that should be normalized and divided by the trace of itself. So that is our final expression, and we'll just use it to compute our equilibrium density matrix when the time comes, but for now we need to calculate this. We generally don't want to compute the steady state density matrix as such. What we are interested in is a steady state value of some observable, and so let's call that observable O, and so the scalar product with O of our steady state density matrix would be the scalar product of this with the same operator O. And well, that's the equation that we need to implement. So what we need to do is we need to get our equilibrium density matrix. We'll assume something about the relaxation superoperator. We really don't have the time in a 1-hour lecture to code up Redfield theory in full. We'll put together our Hamiltonian the way we usually do. We'll pick some observables, and we'll just be doing this inverse. Now what's important is modern numerical linear algebra allows us to compute this particular piece here, that is the inverse of a matrix times a vector, much faster than if we just computed the inverse of a matrix first and then multiplied it into a vector. MATLAB's operator that does it is called backslash, and we'll be using it in order to calculate the things, well, I think in approximately quadratic time with respect to matrix dimension rather than cubic time that it would have taken if we just did the inverse of this first and then multiplied it by a vector. Okay, so let's delete this. We don't need this. Let's delete this. I remember it all anyway. And keep this equation here. And this is the equation that we need to implement. So let's just go ahead and do it. Right, here's my MATLAB window. It's, well, spinach in here. We don't actually use it, but it's just my working directory. So new function, and MATLAB comes up with an empty window with some placeholder here for a function that we're about to start writing. We don't need this, so starting to write it from a comment. So this is a field sweep NMR experiment on a 2-spin system. Okay, written by myself. Right, so function hello world, not depending on anything, closing it. So the first thing to do is to put in the Pauli matrices, and so Pauli matrices, full spin half, sigma x is, as we all know extremely well, 0, 1/2, 1/2, 0. Our sigma y is similarly 0 minus I over 2, I over 2, 0. And our sigma z is 1/2, 0, 0, minus 1/2. So these are Pauli matrices. I'm not testing them. with commutation, because really this is standard and I don't think we've made any mistake typing them. If we did, we'll find out immediately, because generally the propagation stops being unitary if there's some mistake in the matrix, so we'll see something blowing up or going down far too quickly. And we also need our unit matrix, so we'll call it unit, and that will be 1, 0, and then 0, 1. What we now need to do is set up a two-spin system, so two-spin operators. That is, we'll call them L and S, so Lx would be cron sigma x unit, so sigma x on the first spin and unit matrix on the second spin. Ly would be cron sigma y unit, and similarly for Lz, cron sigma z unit, and we just need to copy and paste this and swap a few things around to make for Sx, Sy and Sz. So Sx would have unit on the first spin but sigma x on the second, and similarly for Sy and Sz. So editing these things as appropriate. We could have used crons downstream in the Hamiltonian, but it's a bit more convenient this way. Although technically speaking, in a very, very, very large calculation, pre-computing and pre-storing everything might not be a good idea, but it's just a two-spin system here. Okay, let's save our hello world somewhere. Right, spinach kernel is probably not the right place. Let's get it onto my solid state disk here, disk X. And there we are, there it is. And let's make ourselves a Hamiltonian. So create the Hamiltonian. And what we'll do is we'll assign some chemical shift to the first spin, some chemical shift to the second spin, and put a little bit of J coupling between them. So H is, let's say, 100 times Lz plus 200 times Sz, so 2 Zeeman interactions plus maybe 20 times Lx plus Sx times Sx plus Ly times Sy plus Lz times Sz. So the J coupling, in a real-life calculation you'd have to worry about what values these actually are, they'd have to match your system and so on, but for a synthetic calculation like that, we're just happy with this. Let us also put together a relaxation superoperator. Now, the Hamiltonian here is an operator. We need to make it into a superoperator before we use it. We'll need to stretch the density matrix as well, but the relaxation superoperator needs to be made into a superoperator immediately because it has no image in Hilbert space, and so our R, so relaxation superoperator, would be R, that is I, the unit matrix in MATLAB. And then let's think about what dimension we're gonna give it. We've got dimension 2 by 2 for one spin, so we've got 4 by 4 for two spins, and in Liouville space the dimension squares, and so we need 16 by 16 unit matrix for the relaxation superoperator. And because it's a negative definite operator, we'll have a minus in front of it, and let's make the relaxation rate equal to 2 Hertz. So everything in our system, every single spin order will relax at the same rate of 2 Hertz. Okay, and the Hamiltonian that we've got needs to be also transformed into Liouville space, so super operator. And for that, what we need to do is to cron it up. So our H would be cron the unit matrix of the same size of the Hamiltonian, so I size h times h minus chrom transpose h and then I size h. I is a unit matrix in MATLAB. And that is the Hamiltonian commutation superoperator, and the reason why it's that way has been given in one of the previous lectures that we had. Okay, let's further specify our equilibrium density matrix, so equilibrium state. Because we're in a high temperature approximation here, we cannot really take the Hamiltonian exponential because most of the Hamiltonian is missing because of the rotating frame. So let's just specify it by directive. So rho equilibrium would be our Lz plus Sz. That is both spins on Z, and in order to put it into Liouville space we need to stretch them both into vectors. So that would be our equilibrium state. Okay, so what remains now is to run the simulation, but before we run the simulation we need to specify the kind of perturbations that our system receives. So our perturbation operator, let's call it P, would be Lx plus Sx. So we will be irradiating our system on the x-axis, and we will specify some power for that irradiation. Let's say we are irradiating it with a power of 0.1 Hertz. Yeah, everything is measured in angular frequency units in here, so I guess I should probably multiply everything by 2 pi just to make that explicit. That magnetic resonance simulations always operate in angular frequency units, even though they're nominally specified in Hertz. Pi, well actually J coupling should just be pi for various historical reasons. So R stays in Hertz, but the perturbation strength is also 2 times pi times those things. Okay, so now simulation. We need to loop over the frequencies that our magnet scans. So we will be adding variable amounts of Lz and Sz, which correspond to Zeeman interaction, to our magnet strength. So let's say for frequency, so magnet sweep equals minus, say, 300 to 300 in the step of 1 Hertz. And our Hamiltonian at a given instance in the sweep, so current H would be H plus 2 times pi times magnet sweep times Lz plus Sz. So we are adding a variable amount of Zeeman interaction to our Hamiltonian. So add magnet sweep terms. Then the next thing that we need to do is to run our calculation under that current H, and for that we need the equations that we have derived here. There we are. The observable, for which we will have Lx, Ly and Lz, and Sx, Sy, Sz. So the 3 axes for the magnetization that we've got. Scalar product with this inverse acting upon this vector. So for that we need to find, well, to declare what the observables are. So observables, and obs 1 would be Lx plus Sx, both stretched into Liouville space. And so similarly obs 2 and obs 3 would be Y and Z. 2, 3 real spectrometers cannot really detect on Z, but we don't have that restriction in a simulation, so why don't we do that as well? And we will also pre-allocate, so answer 1 would be zeros, the same size as the magnet sweep, so 601 in this case. 601 times 1, so 600 rows and 1 column. Same for 2 and 3. And our answer, so compute, would be this observable scalar product with this inverse and this R. So why don't we get the matrix inverse first? So get inverse times vector, operation done. So we'll call it something sigma, will be. Now this is where the backslash operation comes in. This is what's it called in MATLAB, and for that, because, well, even I don't remember the exact syntax, we just need to consult the help, so highlight it and bring up the help with F1. So A backslash B is matrix division of A into B, which is roughly the same as inf AB. So we need to put the stuff we are inverting on the left side and the vector on the right side. And so what goes on the right side is our term here. So that's R times our equilibrium density matrix. Notice that I could have pre-computed it out of the loop. It would have been important if we had a very big calculation, but here I think I'll just get away without doing that. And on this side we've got minus IH plus R, so minus 1I times H plus R, and that is our sigma computed with backslash. And then answer 1. Element note that MATLAB does not allow negative indexing, so I'll have to add magnet sweep plus 301 to get it close, well, to get it basically into positive numbers. We'll clean it up in a little bit of time, it's good enough for now. And that would just be observable 1 conjugate transpose times sigma. And similarly for observable 2 and observable 3, and of course this should be current H rather than H, because this current H does actually depend on the magnet sweep variable. So times sigma, and the same for answer 2 and answer 3. 2 and 3. And we'll close the loop. And one important thing to notice here is that this is what's called an embarrassingly parallel problem. That is, 1 point computed on this with a particular value of magnet sweep doesn't actually depend on all the other points, so we are at liberty here to actually parallelize this loop and say par 4. And then individual instances of that loop might be computed on as many nodes as we actually have in our calculation. Now MATLAB warns us here that the variable is not used after the par 4 loop, but well, we'll be using it in just a moment. So plotting, and we just need to plot things, and so sub plot, let's say 1 1 1, so row 1 column 1, 1 row 1 column first panel. Let's make it 3 rows 1 column first panel, then plot real part of answer 1, and then have 2 more panels for answer 2 and answer 3. So 2, 3, 2, and 3. And the warnings disappear, and everything is in the green now, with the exception of one thing. Oh yes, the perturbation operator. We have forgotten to add it to the current Hamiltonian, because it's not just the magnet that is swept, but we are also perturbing the system, and so what we need to add in here is also P. Yeah, that is our full Hamiltonian now, and you see MATLAB's syntax highlighter is now in green, and we can run the sequence now. Okay, pressing run, and looking at MATLAB's window, we got a big error here. Now, don't run to your supervisor, he's a busy man. Let's just read what it says. Matrix dimension must agree. Right, where was it? Par 4 body 42. So going back to our text, line 42, when we were adding the Hamiltonian plus the sweep operator plus the perturbation, the dimensions didn't agree. And the reason they didn't agree is we transformed the Hamiltonian into Liouville space, but we did not transform our perturbation and our other operator, whatever it was in there, yes, the sweep operator, into Liouville space. So why don't we do that? So P is cron size P, and P, and let's just put a sweep operator into a separate variable, sweep operator, and take it out of here, and put it into here, call it S. That would be our sweep operator, LZ plus LZ, and then we can transform it into Liouville space so that matrix dimensions do agree when we add them together. Okay, so our new S would be also S, then S, and S, and we need to replace this with S, and that's our sweep operator. So hopefully something is going to work when we do this again. Now row equilibrium, yeah, we stretched. Our observables we stretched, so well, something should work now. There we are, pretty pictures. So that is our X, I think, that is our Y, and that is our Z. Notice that in the case of LZ we got dips, so it's just a deviation of the magnetization from where it should have been, which is its equilibrium level, 2, and the reason it's 2 is that we've got 2 spins in the system. Then we've got the classical dissipative peaks on the X, I think it is, and we've got the absorptive peaks on the Y, and really it's a tradition in magnetic resonance to plot the things the other way around, so we can just put the minus signs on these two and leave the Z as it was, and there we are. And this is our spectrum, and it looks just fine, except we don't really have enough digitization points here, so why don't we put a few more points around here. And in order to put a few more points, we need to make a few modifications to the way that we have specified our magnet sweep here. This really is a fairly quick and dirty way. What we are supposed to do is first specify the sweep range, and then the loop variable should be something that is, strictly speaking, the point number, rather than anything physical with a dimension, such as the magnet sweep that we've got here. So let's just put this into one line here, this into one line here. Generally things of the same type should occupy a single line in the code. Right, so let's do the following. Let's get our, so let's call this pre-allocate the answer. So we are pre-allocating the answers, otherwise the parallel loop wouldn't work. Then set sweep range, and our sweep range would be, so sweep range will be linspace from right. So we've got it here from -300 to 100. Really what we should be doing here is having a minus, because our sweep is subtracting from the Hamiltonian rather than adding to it. And then let's have our sweep from 0 to 300, but let's have it in 1000 points. Okay, so that's the number of points, in which case we need to put it to 1000 here, and here, and here. And the most consistent way really would be to create the variable called endpoints and just have it everywhere. Okay, so that's our sweep range, and do the simulation. And what we will be looping over is n from 1 to the number of points in the sweep range. And then our magnet sweep here becomes sweep range element n. That goes into the current Hamiltonian, and then answer, this is no longer magnet sweep, this is just n. You see the convenience of these things, and all the error messages are disappearing because we are doing the right thing now. So what we will be doing at the moment, therefore, is having the same sweep, so that it contains our signals, but we will have 1000 points for it, and we'll be doing it in parallel, and parallelization is in our case over the 4 cores that I have on this workstation that we are running this on. Okay, a slightly prettier picture, so you can see the lines are a bit better defined. If we put even more points into here, so let's say 10,000, let's actually create a number of points. Yeah, so experimental parameters, and that will be endpoints equals, let's say 10k. So 10,000. We'll make good use of that parallelization now, and endpoints everywhere where we previously had 1000. And here. There we are. Okay, and let's now look at what MATLAB does. I'll bring up the task manager here, and let's run it and then look at the task manager. So hello world, and switching to the task manager. Well, it really did it so quickly we didn't have the time to see the parallelization working. Modern MATLAB is of course much better than what we had just a few years ago. So 10,000 points were simply done instantly, unless we have forgotten to save something. No, we haven't. So it really did that instantly, and I think now everything should be properly smooth. Yeah, we've got our nice Lorentzian peaks everywhere. Okay, well, let's try making things a bit broader. So if we put our relaxation rate to not 2 but 20 Hertz, what we are going to see is a bunch of broad peaks. If we put it to 0.1 Hertz instead, it would be sharper. So there are various games we can play at this point, but this is basically it. This is a slow path simulation. So what we are doing is we are sweeping not the frequency range, we are not pulsing and acquiring and Fourier transforming, we are actually sweeping the magnet field through the system whilst keeping our X operator wherever it was. The perturbation in the rotating frame just has 0 frequency, so we've got the rotating frame at the frequency of our irradiation, and we are shifting the magnet in the system. Okay, that's about it as far as simulation goes. At this point you should be able, for whatever it is that you are looking to compute, either to write a program yourself or to use something standard like Simpson spin-H or easy spin or spin evolution. Some of them are closed source, some of them are open source, but everything is well documented, and at least that'll get you started. One problem that I would like to mention as a part of this course as well, because it happens so frequently, is a situation where you need to simulate something for which The interaction parameters, such as chemical shifts, hyperfine couplings, distances, geometries, you name it, are simply not known. Or there is no literature that lists it, or it's published in some obscure journal that the Soviets have printed in 1945 and nobody has since seen anywhere on any bookshelf. So we are faced with a problem of estimating a magnetic parameter, of finding out what a particular shielding tensor might reasonably be, even if we don't have, at least for a moment, perhaps some resources to measure it. And this is where quantum chemistry comes in, and this is where Gaussian in particular comes in. Now, if you don't have this program as a part of the university site license, do pester your supervisor to purchase it, because it's absolutely amazing. I mean, there are various open source alternatives, but really your time is also precious. And insofar as the balance of getting work done versus time spent is concerned, Gaussian really has no particular competition. This is Gauss views that I've got here on the screen. It's a graphical user interface. So let's say we're interested in computing the chemical shielding tensor of the middle carbon in fluoropropylene, which, well, it might take us a while to dig out of the literature, and I suspect just simply is not there. So why don't we draw ourselves propane? There we are. Kill a few hydrogens in here to make it propylene and put a double bond in the middle so that it really is. Clean up the structure a little bit. There we are. And then stick a fluorine somewhere just for the hell of it. That's the fluorine, and let's put a fluorine into this position. So we might be interested in the question of what is the fluorine line width in this molecule. What we need to know, therefore, is what is the rotational correlation time, and, well, roughly the radius and the geometry, but that can be estimated from just looking at it. So say our primary radius would be the distance from here to here. That's about 4 angstroms. So the Stokes-Einstein law might give us a reasonable estimate of the rotational correlation time, but we need to know what the shielding tensor is here. So the two things we need to do here is first to optimize the geometry with DFT or post-Hartree Fock or whatever we choose. It's a small molecule here, and then to get the shielding tensors. And just for the hell of it, I guess let's put a nitrogen into here, a nitrogen 14, so that we might also, for various reasons, in particular because the quadrupolar coupling in here might be significant, would want to have a quadrupole tensor on the nitrogen as well. And because we are going to run a spin dynamics simulation on this, we'll also want the J couplings. So, in order to do relaxation theory, we need to know all the coordinates, all the shielding tensors, and the quadrupolar tensor for the nitrogen 14. In order to actually compute that, we need to do a geometry optimization followed by the calculation of all of those parameters. So, well, let's just quickly run through that. So, calculate Gaussian calculation setup. There's a big window here. First of all, geometry, tight convergence criterion method, say DFT, the notorious B3lib, don't use it, just find out what works in your particular case, it's a much better idea. 631G, DP, Popple's classical basis set, charge 0 spin singlet, it's a neutral molecule, let's do it in vacuum. No title, we don't need it. General, some additional information is always useful. And everything else we'll just leave it at default. So submit, save, let's just save it somewhere. This is as good a place as any. Well, I guess I'll probably put it into the same X that we had here. So geometry, and that will save us. Submit to Gaussian, yes please, and there we are. There's Gaussian window running, doing our optimization. We might have specified a few processors that would have run in parallel. So there we are, the first iteration is done. Running the second iteration, converging the self-consistent field in there. It might take it a couple of minutes. So what's happening at the moment is Gaussians calculating the DFT energy, calculating the gradient of that energy with respect to the atomic coordinates, and just taking a quasi-Newton step down in the direction where that energy is going down to get the set of atomic coordinates which correspond to the local energy minimum. We've specified tight tolerances there, so it might take it some time for it to actually get there. But the fact that it's only taken just 5 cycles to converge the self-consistent field in there means it's probably getting close somewhere to the final convergence. It will tell us when it does finish. Okay, we are done. Gaussian prints a fancy quotation at the end of each calculation, so we can close it, and it comes up with an offer to open us the file. There we are. That's our new geometry that's been optimized. You see the nitrogen got a little bit flatter here. So our next stage is to run NMR parameters on this. So job type NMR, gauge independent atomic orbitals, compute spin-spin couplings. Mixed is a certain type of basis set alteration, always a good idea when we are computing the J couplings. More on that actually in our quantum chemistry course that's on the same website as the spin dynamics. And we also need additional print keywords that will get us the quadrupolar tensors for our nitrogen output pcat. That used to be a program that did the magnetic resonance simulations, but I think it's no longer supported. But well, the output type is still there. Right, that's it. I think I'll choose a slightly smaller basis set now. Typically we would like at least CCPVTZ, but really for the purposes of a fast calculation, let's just have it as 321G. That should be fine. At least, well, the calculation will run and produce some approximation to the result, if nothing particularly accurate. So it's a big field, just to be clear, the calculation of magnetic parameters. So we are using one of the simplest methods out there. Do look at our big quantum chemistry course for further particulars on this. Okay, so submit, save, and let's just say magres. And submit. Well, before we submit it to Gaussian, let's just give it a little bit more memory. So memory limit specify a couple of gigabytes and 4 shared processors, just to make it a little bit faster. So submit magres gjf, file exists, submit to Gaussian. Boom. Wouldn't want to do that. Didn't like our 2 stars on the basis set. Probably not a supported syntax, so let's just modify the job description to just have 321G, which is definitely a supported basis set here. So exists overwrite, exit and run, and there we are running. So again, it might take a certain amount of time to get processed, so let's just wait and see for it, wait for it to complete. Okay, we are done. So now let's look at the log file. Let's just close both this and Gauss view and just open our usual file navigation thing and get us here. So magres log, and that's just a Gaussian log. It's a fairly big text file, but what's important is that it contains all the parameters that we want. So nuclear quadrupole coupling constants in megahertz. You can see zeros, of course, for carbon 12, zeros for 1H, zeros for 19F, but we have a non-zero full tensor 3x3 Cartesian matrix for the nitrogen 14. Then there's a spin rotation tensor for those of you who are interested in spin rotation coupling. There are tiny numbers really here for protons, fluorine, nitrogen, and so on. If we scroll a little bit further up, what we will discover is total nuclear spin-spin coupling in hertz. so between every nucleus and every other nucleus. Don't treat these parameters as precise. Even at the highest levels of theory, it is at best an approximation. At the small basis set levels that we've computed, it's probably only correct to about an order of magnitude. If we did use triple zeta basis set with sophisticated exchange correlation functionals, then it may be accurate in good times to about 20%. It's not extremely good, but it's something. At least for a molecule that literature knows nothing about, it's some place to start. Quite a few estimates may be done with just these values. So scrolling further up, we get to magnetic shielding tensors, and we got them for all the nuclei here. Gaussian simply assumes the nearest magnetic isotope. So for carbon, that would be carbon 13, for hydrogen 1H, for nitrogen 14N, and for fluorine 19F. And there we are. Now, what's important to understand about shielding tensors is these are what's called an absolute shielding tensor. That is, they're referenced not to TMS, not to any specific chemical substance. They are referenced to the bare nucleus in vacuum. So they are absolute shielding of that electronic structure that's around it, as compared to the total absence of electronic structure whatsoever. So to just a nucleus without the electrons around them. And so in order to get it relative to the TMS, we would need to calculate TMS at the same level of theory and then subtract the two numbers. So again, you've got here full 3x3 shielding tensor that can be used in relaxation theory calculations, for example. You can just cut and paste it into your own calculation. Spinach has got the commands that can read these Gaussian logs directly and just import the data from there. The graphical user interface we are working on also does read them automatically, but well, the numbers are all here for you to use if it becomes necessary. And if we scroll somewhere further up, we will see all the coordinates. You've got this standard orientation section. What's important is when you do a molecule geometry optimization or magnetic resonance calculation in Gaussian, it does change the coordinates. It translates and rotates the molecule into the eigenframe of the inertia tensor. And all of the magnetic couplings that you saw below are actually written in the same frame as this so-called standard orientation. So don't use the input orientation. There is the standard orientation that all the interactions are referring to in their specific Cartesian form. Okay, so that's just a quick introduction into Gaussian. More on that in our quantum chemistry course. It's very useful in practice. For many molecules, it's not necessary to know things precisely. For many molecules, it's too tedious to do the experiment. And so running a quick DFT on them will in many cases be sufficient to convince you that something is possible, something is not possible, or exclude a particular relaxation mechanism, or just make some reasonable conclusions about what it is that you're looking at. Okay, that's the end of the lecture, and I'll see you all in Warwick at the workshop.